many?
এতিয়ালৈকে স্যার আপোনাৰ 7 জনের বাকি আছে।
Okay.
So start করব।
Okay. Good afternoon, everyone present here. This is D. Chakraborty from IIT Guwahati. I'm very happy to come live because all these days it was all monotone. I mean monologue. You know, I have been only telling and there was no interaction. But so what I'll do is I have planned this live session as because some of you have already put certain doubts in the after seeing the videos. There are I think 6-7. So I'll go one by one, and plus there are some live questions also I could see in the chat box that also I'll address. And some of you have requested that I do actually discuss some problems of the assignment that I'll do at the end. Maybe last half an hour I'll do that. Is that okay? I think they can. They cannot
speak, sir, because a large number of people are there.
But suppose somebody wants to speak.
Yes, so that they will actually start box, sir.
Okay. So I'll go one by one. So let us see the first question. That is can we just see that video? Yeah, this question one. Yeah. Okay, otherwise I'll write this. Is it okay? So just go forward a little bit. Little bit more forward. But stop. So next. Yeah. So one of no next. There is a relationship between the reduced stiffness Q and the stiffness matrix C. Next. Just go a little forward, little more. Next slide, most probably. Bas, this one. So you have yeah. So one of you have written that why this IJ is going from 1 to 6 because I mean C66 and Q66 are equal. You can see if you put 1 that is C11 minus C13 into C13 divided by C33. If you put 2 that also satisfies. If you put 1 that also satisfies. Now anyway Q16 is 0, Q26 is 0 because C16 C26 are 0 for orthotropic lamina. And then when it comes to Q66, there is nothing like C63 and C6, therefore that is anyway 0, therefore Q66 is equal to C66. So it's correct. I and J goes from 1 to 6 to take care of the fact that Qij could take the value of 11, 22, 12 and 66. 1626 is anyway 0 for orthotropic lamina. So I'm coming to the next question that next link, yeah. Yes. One of you have asked why sigma x is equal to sigma x dash. Why sigma y is equal to sigma y dash. You can see, just can I go to the slide before? If you see how we have defined this monoclinic, that means there is one plane of material property symmetry. Now please recall that what exactly is material property symmetry. That means with respect to that plane, if you rotate this by 180 degree, there is no change in the stiffness or compliance matrix. Okay. Now what we have done is, just go back to the previous slide, or maybe I'll write, yeah. So what we have done is, we have done the stress transformation and strain transformation by this direction cosine matrix when we have changed x3 to x3 dash, that means 180 degree rotation with respect to that plane, okay? And then after doing this stress transformation, we have seen that sigma x dash and sigma x is exactly equal, it does not change, okay? Tau xy dash and tau xy is also same. Only thing that changed is tau xz becomes minus tau xz, okay? And tau yz becomes minus tau yz. Other stresses are same. Therefore, this is how, if you take the stress transformation by rotating this x3 to x3 dash by 180 degree, this is the new stresses with respect to the new coordinate axis, that means x1, x2 and x3 dash, okay? Now, what happens is, even if we do this transformation, the stiffness does not, that C matrix does not change, okay? Next slide, next, yeah. Therefore, you see now what we have done, because we know that sigma x and sigma x dash or prime are same, therefore we equate this, and in both the cases with reference to the first axis, that means x1, x2, x3, and with respect to the transformed axis, that means x1, x2, x3 prime, that C matrix does not change. Therefore, we have used the stress strain relation using the same stiffness matrix, and we have equated sigma x is equal to sigma x prime, similarly sigma y is equal to sigma y prime, and from there we could see that when we come to these two equations, that obviously C15 and C14 goes to 0. So I think I am clear why sigma x is equal to sigma x dash and sigma y is equal to sigma y dash, because we have performed the stress transformation and strain transformation, and we have seen that these stresses remain same even if we change the coordinate axis from x1, x2, x3 to x1, x2, x3 bar. I think I am clear. If not, you may please write back. I can again tell that. The next is, someone have asked, what is E by density and ultimate tensile strength by density? Yeah, in this table you can see that, say for steel and graphite fiber, the idea is to actually compare the specific modulus. What is specific modulus is, suppose the two materials have the same, say, Young's modulus, but one is much lighter compared to the other, okay? The density of one is less than that of the other. So what is specific modulus is, we divide Young's modulus by the density, and that shows that between the two materials having the same stiffness or the same Young's modulus, which one is lighter, okay? That means weight. So in weight specific application, it is more important to know specific modulus rather than just modulus. Say for aerospace applications where weight minimization is very, very important, what we do is we look for materials which not only have the good strength and stiffness, but it is lighter. So a measure of that is specific modulus. Similarly, specific strength is, suppose we have two materials having almost same strength. Now one which is lighter will have more specific strength, okay? That means we have the material with same strength, but one is lighter than the other. So that is actually measured by specific strength. So E by rho actually gives us the specific modulus, which is an indication of a material having sufficient stiffness but lighter, and sigma u by rho is the specific strength, which shows that we can compare two materials having, say, similar, almost same strength, but one is lighter than the other, which is important for weight applications where we want weight to be minimized. So this is what is E by rho and sigma u by rho. That means specific modulus and specific strength. So the next question is, 4. What is the difference between engineering constants and elastic constants? I think I have specifically spelled it out. Like what we have done here is that we have written the Hooke's law for different, say, for an anisotropic material. So we have written the generalized Hooke's law. That means stresses are linear functions of strains, okay? And those elements of the matrix C11, C12, these are the elements of the stiffness matrix, okay? Or these are also called elastic constants. Like we have seen, for anisotropic we need 21 independent elastic constants. On the other hand, for isotropic material we need only 2 independent elastic constants, and in between there are orthotropic materials. So this is elastic constants, okay? Now what are these elastic constants? What we do? I told already that we have discussed that given the stress, I can find out the strain and vice versa. But who will give us this C11? So engineering constants are the measurable physical quantities. Like C11 is actually function of E1. Okay. Say for isotopic material, what are the engineering constants? Young's modulus and Poisson's ratio. Okay. Other one is the shear modulus, which is of course a function of Young's modulus and Poisson's ratio. Similarly, for orthotropic materials also, the measurable engineering quantities are Young's modulus along 1, Young's modulus along 2, Young's modulus along 3 Young's moduli. Okay, these are 3 engineering constants. Similarly, we have Poisson's ratio nu1 2, nu2 3, nu3 1. These are also engineering constants. Okay, and G1 2 shear modulus, G2 3, G3 1. These are measurable engineering quantities, which actually decides what will be the value of C11, what will be the value of S11, what will be the value of C22. Okay, so this is what is the difference between engineering constants and elastic constants. Engineering constants we measure in the laboratory, okay, and from those engineering constants we can actually construct what you call elastic constants, or we can construct the stiffness and compliance matrix. I hope this is clear. If not, you may write in the chat box. I'll see. Yeah, next question is, what is cross-linking? As I told that, I have just briefly introduced you about the composite materials, okay? But the polymer itself has many things which I have not discussed here, okay? I have just told that thermosetting and thermoplastic, polymers, okay? Matrix materials. Now, cross-linking actually provides, in the polymer chain, it provides some cross-linking, thereby making it stronger, so that what happens is it can actually withstand more temperature. It does not get easily softened under temperature, okay, and it becomes a thermoset plastic, okay. So beyond that, if you want, you can see books on polymers, but since the objective of this course is to understand mechanics, I have not gone into details of this. Of course, neither I am an expert in this polymer science. Therefore, in brief, this is what is cross-linking is done to make it more strong, and it can withstand more temperature. It does not get softened very easily. That is what is cross-linking does in a polymer. Next question is, please go to that 6. Yeah, in this, thank you for pointing out. This is a typographic mistake. In this S matrix, it should have been minus nu xy by x and minus nu y x by ey. Okay, it should have been like this. Somehow this minus sign does not appear. So we have actually corrected it. I suppose some of you might have already received the corrected, corrected slide. Okay, this should be minus. Okay. So can I write here? Can I write? No, not here. I mean in this. So I'm just writing that thing. So thank you for pointing out this minus. Somehow it was a typographical thing and it was missed. So we have already corrected the slides and some of you might have received the corrected slides. This is what it is. Yeah. Can I see the chat box? Is there any related question here? Okay, elastic constants, engineering constants I have already done. Kindly discuss question 4, 5, 6 from assignment. You will see that. Okay, also explain the details what is the glass transition temperature. I will come to that. Okay, the next question number 7. Not question that. There is doubt. Number 7 is there, no? Yeah. This one, yes, yes. Oh,
it's from the course.
Oh, course. Okay. I think I'll write that. I'll write that.
Okay, so
let me see whether what did I? Another paper. Actually, the second page is the second page. 4, 5, 6, 7, 8, 9. I missed that.
what is our week, sir? It's from which retreat?
I think module. No, week 3. Week 3. Just wait. Week 4. Failure. Staying failure part 2. This one. Yes, yes, yes. Yeah. Go first. Next. Bus. So one of someone asked that what is the difference between x1 and x2? You can clearly see, but before that I must tell you that there is again a typographical mistake. It will be tau 1 2. This will be actually positive, tau 1 2 square by tau 1 2 u square. I mean sigma 1 by sigma 1 t square, sigma 1 2 by sigma 1 t 2 square. This is minus, next is plus, but final term is also plus. Also it should be positive. Okay, it is it is correctly written in the second thing. Okay, so now what is the difference between x1 and x2? I'll tell you. Just I'll write. Just follow me. I'll just write here. So it was something like this. The Sahil theory, sigma 1 by sigma 1 tu square plus, sorry, this is minus, sigma 1 sigma 2 by sigma 1 tu square plus sigma 2 by sigma 2 tu square plus, this was actually wrongly written as minus, actually it will be plus tau 1 2 u square. Okay, this was the Sahil. Okay, now you can see these two terms, this term sigma 1 sigma 2 are actually interactive terms where the combined effect of sigma 1 and sigma 2 are there, but what happened there was that the sign was not considered. Okay, because if you look at this, what are the numerator denominator? In every case the denominator is actually the corresponding strength, but here in for both sigma 1 sigma 2 it is sigma 1 tu square, irrespective of what is the sign of sigma 1 and sigma 2. So what is done is it was modified like this: sigma 1 x
flip. Ulta koi submit.
Oh no, that's fine. So can I see this?
Yes.
Yeah. Sigma 1 x1, sigma 1 by x1 square minus sigma 1 sigma 2 x1 x2 plus sigma 2 by y square plus tau 1 2 by s, right? S square. So this x1, if sigma 1 is positive, now it takes care of the sign. If sigma 1 is positive, x1 takes the value of longitudinal tensile strength. If sigma 1 is negative, x1 takes the corresponding compression strength. Similarly, since this x2 is corresponding to sigma 2, therefore if sigma 2 is positive, x1 takes the value of sigma 2 tu. If sigma 2 is negative, x2 takes the value of sigma 2 cu. Can you just go to that slide? So this is what is written here. You can see, okay, that x2, if it is positive, then if sigma 1 is positive, it takes the corresponding positive strength, tensile strength. If sigma 2 is negative, it takes the corresponding compression strength. So that is what is the difference between x1 and x2. It takes care of the sign of this sigma 1 and sigma 2. Okay, so next question is that go to this, the question is why the compression part is not taken into account. Okay, the compression part is, see, basically here we are trying to find out the longitudinal tensile strength. Now if you look at the maximum shear stress criterion, there are, as I told, there are 5 different criteria actually. So depending upon the sign of depending upon the sign of sigma 1, say in this case, can I go to this, writing this thing? Yeah, so you can see this is sigma 1 cu, sigma 1 tu. Okay, similarly sigma 2 tu, sigma 2 cu. Now in this case you can see sigma 1 is sigma x cos square theta, sigma 2 is sigma x sin square theta. Okay, because sigma x is positive, therefore this is always positive, this is also positive, and since these are positive, so we are only comparing this sigma x cos square theta is less than sigma 1 tu and sigma x sin square theta is less than sigma 2, sigma 2 tu, because both are positive. Had it been negative, we would have come to this side. Therefore the compression part is not taken into account, and here the objective is to determine the off-axis tensile strength. Okay, therefore since its off-axis tensile strength, therefore sigma x is positive, and sin square theta cos square theta is anyway positive, therefore it takes only positive value, and therefore it is only compared with that. Okay, and similarly here it is sigma x sin theta cos theta tau 1 to u. Okay, because here the sign doesn't matter. Okay, it is the magnitude of sigma x sin theta cos theta, and it is actually compared with tau 1 to u. Yeah. Next, yes, go to that please. No, not this. Is it this? Just let me read that what is written. Hello, it is mentioned that the transverse compressive strength, longitudinal compressive strength, transverse compressive strength. Slightly it was mentioned that transverse compressive strength, longitudinal compressive, but here it is. Is it the discrepancy? What is that? Just go to that. Oh, okay. Actually, yeah, go back somewhere. I think I have. Not in this slide, actually. Just, yeah. Actually, in this slide, the longitudinal compressive strength is less than transverse compressive strength. That was again a typo. It's a mistake, actually, you know. Actually, I wanted to write two things, but it got clubbed. Actually, it should have been longitudinal compression strength is less than longitudinal tensile strength, and transverse tensile strength is less than transverse compressive strength. But somehow this got clubbed, and therefore I think this slide has been corrected already, and the corrected slide has been sent. Okay, I will also correct this in the video. Okay, so it will be, you can read this as longitudinal compressive strength is less than the longitudinal tensile strength, and there will be another line that the transverse tensile strength is less than transverse compressive strength. Somehow these two got clubbed, and this is wrong. Longitudinal compressive strength is not less than the transverse compressive strength. That's what created confusion. So I have corrected this, and the corrected slide has been sent. Okay, please read it like this. Maybe I can write just, yeah. That longitudinal compression strength is actually less than longitudinal tensile strength, and transverse tensile strength is less than transverse compression strength. And already we have written that the transverse tensile strength is much less than longitudinal compression strength, and therefore the transverse tensile strength is the weakest that we have discussed already. So please read it like this: longitudinal compression strength is less than longitudinal tensile strength, and transverse tensile strength is less than transverse compression strength. Instead of that one line, there should be two lines. Okay, well, we'll send you the corrected slides also. Yeah. Next, any other question was there?
No.
Yeah. So this is done, and there are two questions already. One question is that in the Excel file, there are two questions I have seen. One is whether in the exam, do you need to convert that transformation of Q to Q bar or S to S bar? That Excel file, somewhere it is there. Which software are used in the analysis of lamina? As such, we are not using any software for analysis of lamina right now. But you can, if I have intentionally not introduced any programming part in this. But having said so, many of these, these calculations are ideally not suitable for doing by hand. So you can use any software. You can write a code, a small code, or you can use MATLAB. That doesn't matter. But the main objective of this course is to understand the mechanics. Therefore, once you understand the mechanics, you understand clearly the steps, basically the analysis of a lamina, and then, of course, we have not come to that yet, analysis of laminate. Then you can use any software and you can write your own code. But it's important to understand the mechanics. How from a given load we compute the stresses, we compute the strains, and apply the appropriate failure criteria. Okay, once we understand that, other things will be easier, in my opinion. You can do that. So as such, we are not using any software right now. Then the second question is, for the calculation of Q bar from Q, will the formula be provided in the exam? Please note that exam, it should be very, very clear. we don't expect you to by heart any formula, or we don't expect you to remember this transformation matrix and all. No. Okay, whatever formula are required will be provided. Okay, and even the calculations will also be kept minimum so that you can do using your virtual calculator. Okay, again the emphasis will be given on the understanding of the mechanics of this material, mechanics of this composite materials. Therefore, be assured that in exam you don't have to remember any of this formula, this big formula. These are okay. The stress transformation, transformation, stiffness transformation, the relation between Q and Q bar, S bar and S. You don't have to remember anything. Wherever it is required, we will give. Okay. Of course, some of the basic formula you are supposed to know. Say for one dimensional, say, can I go to this thing? Just
PPT.
Say we expect you to remember this. Say for one dimension, stress is equal to Young's modulus into strain. This you are supposed to remember. Similarly, for two dimensions, suppose epsilon is equal to say sigma, okay, by E, okay, and say suppose there are two stresses, suppose epsilon x and epsilon y. So this is sigma x by E minus nu sigma y by E. These things you are supposed to remember. This is nothing to do by heart, because if you understand the stress strain, if you understand what happens when you apply a stress to the strain, these are not formula which you have to keep by heart, but you can. So this I expect you know. Okay. Similarly for say three dimension, you know, epsilon x is equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. Or for an orthotropic material, I think the basic, you know, epsilon x by E, okay, minus nu yx into epsilon y by EY. So these things you don't have to remember, but I am sure if your understanding is clear, you can write this. Other than that, all the formula, whatever AS, S bar, stress transformation, strain, all this will be provided. So don't bother about this. The exam will not be to judge how well you remember the formula. Exam will be mainly to judge your concepts. Okay. There was another question, I suppose. Why stresses for the fiber and the matrix the same when we determine the transverse Young's modulus? Okay, let me go to this. Yeah. We have taken a representative volume element, right? In the representative volume element, we have, suppose this is one fiber surrounded by matrix. So this is direction 1, this is direction 2, okay? So we apply a force here. So you are asking, this is matrix, okay? And one fiber surrounded by matrix. You are asking why the stress in the fiber and the matrix is same. You tell me, but under all the assumption is that these fibers are uniformly spaced, all these assumptions are there. Under this assumption, you tell me what is the stress. If we apply a load F in this direction, the stress is nothing but force per unit area. So whether you are here, whether you are here, whether you are here, the area is same. Therefore, the stress in this direction, sigma, whether it is matrix, whether it is fiber, whether it is composite, is same, isn't it? They are shared equally. But suppose, this fiber is not throughout this, then it will not be. Suppose the fiber is only up to this, okay? In that case, this will not be true, okay? But in this case, the fibers and the matrix in the representative volume elements are actually equally spaced, and the fibers are throughout the length of this. The matrix length and fiber length are exactly same. Therefore, the stress is same, isn't it? But the strains will be different. You know, total elongation in this direction will be elongated, due to the fiber plus due to the matrix. Unlike in this direction, when we have done for one, in this direction, okay? In this direction, the strain is same because they are perfectly bonded. They are perfectly bonded. Therefore, they are not allowed to stretch by defined amount. Therefore, the strain is same, okay? Whether it is the fiber strain, whether it is the matrix strain, whether it is the composite strain, it is same. but the stresses are different, isn't it? Because the load is now shared by this. A part of the load is shared by the fiber, a part of the load is shared by the matrix. Therefore, the stress in the fiber is FF by AF. Stress in the matrix is FM by AM. Okay, and stress in the composite is, of course, total F by AC. F is nothing but FF plus AM. Okay, so that is why the stress here is same. Stress in the fiber and the matrix is same. Is that clear? Can you just tell me in the chat box if that is clear? So assignment number 3, question number 4, 5, 6. Somebody has asked. Assignment number 3. Let me see what was.
Yes, sir.
Yeah. Just I have this. Yeah. Question number 4, 5, 6. A unidirectional glass epoxy lamina is loaded in an UTM along direction 1 and the corresponding increasing stress values, the strains along 1 and 2 are recorded using this. Okay. So the longitudinal Young's modulus, the major Poisson's ratio, and the lamina is now subjected to biaxial normal stress, the longitudinal strain. Yeah. So I'll just solve it. Just look at this. Next, yeah. So it's given that the stress these 3 values are given. See, basically in a tensile test, what we do is we have a specimen. Suppose this is okay. So there is a strain gauge along 1 which records the strain along 1. There is another strain gauge which records the strain along 2. Okay. So if you plot the stress versus strain, this is what you get. I mean, this is nothing but number of points joined. Okay. So sigma 1 versus epsilon 1. You load along 1 and you get the strain along 1. So there will be also strain along 2 because of the Poisson's effect. Maybe that strain is like this. It will be negative, isn't it? It will be so the strain in this case will be negative. Okay. So I think I have given here, say the data are given. So here, say corresponding to these strains, epsilon 1, there will be, this is epsilon 2. Okay, you have the values of epsilon 2. I am showing in one diagram. You may actually put another diagram. Okay, say corresponding to epsilon 1, you can put this epsilon 2. So this line will give corresponding to epsilon 1 what is the epsilon 2. Okay, so you have these values 25 minus 6.25, okay, 50. So all these, I am not repeating this, you know. So what is the definition of Young's modulus? Young's modulus is nothing but the slope of this curve. What is this Young's modulus? Because the stress is along 1 and the strain is along 1, therefore this is U1. U1 is nothing but sigma 1 by epsilon 1. Okay. How the Poisson's ratio is defined? When you load this along 1, you take a specimen, load this along 1, okay, that means you apply only sigma 1, there is no other stress, sigma 2 is 0, there is no shear stress, tau 1 2 is 0, then what happens? Definitely there will be epsilon 1 and there will be epsilon 2 because of Poisson's effect, and the Poisson's ratio is defined as nu 1 2 is the ratio of negative of epsilon 2 by epsilon 1 subjected to this condition. That means only sigma 1 is not equal to 0. Okay. So from this data you have I think this is epsilon 2. This is sigma 1. Sigma 1 is 25. Epsilon 1 is sorry, I think sigma 1 is 1 MPa. Epsilon 1 is 25 micron. I am not writing the unit. Okay, and epsilon 2 is minus 6.25. Again, then we increase it to 2 megapascal. This is 50 micron, and this is minus 12.5. Okay, so from this you can straight away find out what is the Young's modulus. Okay, Young's modulus is stress by strain. This data actually represents a linear set. You can see it linearly, proportional. Okay, therefore from this you can find out that corresponding to the stress by strain 1 megapascal divided by 25, this gives you 40 GPa, or 2 megapascal divided by 50, same. This is the Young's modulus, and the Poisson's ratio is nu1 2 is negative of epsilon 2 by epsilon 1. Okay, so if you put this becomes minus 6.25 divided by 25, or you can take any other value, minus 12.5 divided by 50, and this gives you the Mazur-Poisson ratio as 2.5. Okay, now this Lamina is now subjected to biaxial nominal stress. Sigma 1 is equal to sigma 2 is equal to 2 MPa. Therefore, what is the longitudinal strain? That you can find out, right? Sigma 1 by U1 minus. So from this you can find out straight away what is the strain along 1. Okay. Is that clear? Or any other? So, any other question? What is the time now? We have some time?
Yeah, around 5 minutes.
Yeah. So, I'll just see, even from the, I'll tell you another thing, that in your assignment we have given some problems which are little lengthy, okay? But the objective has been again, so that you practice those problems. I mean, in exam we will not give such lengthy, questions, because it is not that, it is not easy to do that without pen and paper, okay? So in exam, but again, those concepts will be useful, okay? So that you can do using your virtual calculator, and as I told, you don't have to remember any of these big formulae, okay? All these required formula will be given, okay? Whatever, but excepting some basic concepts, all other formula, whichever is required, essential formula will be actually provided. So any other, this thing, let me see. So I'll just just come back to this. Yeah. Let me see some. Say, if you look at assignment 4, say let us take any one of these problems from assignment 4. Say problem number 5 from assignment 4.
Due date is not over, so you may not reveal the answers.
Assignment 4 is done, no? Week.
Due date is tomorrow is the last date for the assignment 4.
Oh, then I'll not do it. No, but this is week 5, no? We have already given assignment 5.
Yeah.
Week 4. Okay.
So it may just
okay. Anyway, so no, I'll not. Let me just So for any see in macromechanics, whenever you have to actually find out the strength of any lamina, I'll just tell you the steps again. This is important. What you do is, I have maybe in your video lecture it is there, but I was a little fast there, so I'll just suppose it is subject any lamina for that matter, okay? It is subjected to all kinds of stresses. So this is your material direction 1, 2. This is x, y. Suppose it is subjected to, with respect to x, y, it is subjected to sigma x, sigma y, tau x, y. Therefore, what you do is immediately you find out what are the material axis stresses. Sigma 1, sigma 2, tau 1, 2. How you do that? You know that the transformation matrix, which is nothing but a function of theta. Again, you don't have to remember this transformation matrix, that will be provided. So you can find out the material axis stresses. Okay. Once you find out the material axis stresses, suppose you want to use any appropriate failure theory, say maximum stress criteria or say Psi-Hill criteria, just put this in that criteria and then decide whether it is safe or it has failed. Safe. So the main thing here is, given the stresses with respect to the global axis, you can actually immediately transform it to the material axis, okay, and then compare these material axis stresses to the corresponding strength. Say if you are applying maximum stress criterion, this sigma 1 should be compared with sigma 1 Tu if it is positive, of course. If it is negative, it has to be compared with sigma 1 Cu. Then sigma 2, if it is positive, it has to be compared with the corresponding strength, that means sigma 2 Tu. If it is negative, it has to be compared to sigma 2 Cu. Similarly, tau 1 2 should be compared with the corresponding in-plane shear strength. It is of course independent of sign in the material axis. I have repeatedly told that. So basically, given the state of stress, you find out the material axis stresses and then compare with the corresponding strength. Okay, or if it's a interactive criteria, say Psi-Hill criteria, you just put those values in that expression, and if it is less than 1, it is safe. If it is equal to 1 or greater than 1, it is not safe. So any other question? Solution numerical factors have been okay. Solutions will provide. Thanks for the clarification so far. The question is with respect to the Psi-Hill theory. My question is with respect to the interactive term, the sigma 1, sigma 2. Yeah, sigma 1. Yeah, sigma 1 ultimate strength and not the ultimate strength of sigma 2. I think I have told that already, that because in the original Psi-Hill theory, it is sigma 1, sigma 2 divided by sigma 1 T square. Therefore, it is immaterial what is the sign of sigma 1 or sigma 2. It is always sigma 1 Tu. To get rid of that, what is done is, if sigma 1 is positive, then it is sigma 1 Tu, which is x1 takes that value. If sigma 1 is negative, x1 takes the value of sigma 1 Cu. Similarly, if sigma 2 is positive, it takes the value of sigma 1 Tu. If x2 is negative, it takes the value of sigma 1 Cu. Just to take care of the sign. That means the strengths are changed according to the sign. Okay, if it is still not clear, because maybe I am running short of time, you may write an email. I will just write back to you in details. Okay, if you have any other thing. I think that's allowed, right?
Yeah.
So you please write me an email. I will write in details. Any other question? Just at the bottom. Let me see. Book name, I think in the beginning I told, you can see Cause book, you can see R.M. Jones book. I think I told you the name in the very beginning. Mechanics of Composite Materials by A.K. Kaur and by R.M. Jones. Okay. The first slide, it must be there in the this thing. No, not here. Actually, in the first this thing.
Yes, I got it.
I see that the name of the books are there. R.M. Jones, Arthur Kaur, Daniel and Ishai. For problems, you can see Daniel and Ishai. There are a good number of problems are there.
Okay, then one
So,
more question is
sir, please send your email ID. My email ID is there already, right? In the
yes,
site.
I can also be emailing. Can I put your email?
I'll write.
Okay, sure.
It is there.
Just a minute, just wait.
My email ID is Chakra, CHAKRA @IITG.ac.in. Okay, you can write email to me. Sir, why cannot we consider general orthotropic material same as anisotropic material? Because the general orthotropic material also exhibits stress extension coupling. I think I told you general orthotropic material appears to be anisotropic because there is shear extension coupling. It is actually not anisotropic. In fact, there are planes of mutually perpendicular planes of orthotropy, but what happens is if you can locate that, then if you apply load with reference to that plane, it actually behaves as perfectly orthotropic. Okay, otherwise you take a lamina and you apply load in any other angle rather than the principal material direction, it behaves as an anisotropic, but actually it is not anisotropic, it's orthotropic, provided you can identify the planes of orthotropy. If you can understand, if you can locate the planes of orthotropy, this is perfectly orthotropic material. It's an orthotropic material. Okay, like I think I gave you an example also. If you take any object and if you remember your moment of inertia, that with reference to the principal axis, the product of inertia vanishes. Okay, so but until unless you know the principal axis or principal planes, you will not be you feel that the product of inertia is there. With reference to any other axis xy, the product of inertia will be there. But if you can locate the principal axis and then find out, then the product of inertia will go. Like in case of an any loaded object, with reference to principal axis in the stress, the shear stress is not there. Okay. So similarly, this is a generally orthotropic material which apparently or seemingly it is like an anisotropic material, but it is actually orthotropic. Okay. Provided you can locate the directions of orthotropy. That is why, even though there are six elements in the reduced transform stiffness matrix, but only 4 of them are independent. Okay, only 4 of them are. Those 6 S11 bar, S12 bar, S16 bar, S26 bar, S22 bar, S66 bar could actually be expressed in terms of 4 independent compliance terms: S12, S22, S12, S22, S12, and S66 and theta. So there are actually 4 independent elastic constants. Is that clear? Okay. Maybe you can still come with some of this in the next session. So
He'll also take in his course discussion forum.
Even in course discussion forum, I think if you write, we'll reply. Yeah. And what is this? Is it once in a month, this live session?
Yeah, for technically it's once in a month, but if you want it, you can also.
I can do twice a month also, yeah. Right?
It's like up to you. Sir.
Okay, I can do fortnightly also.
Yeah, it's up to you. Sir.
Okay.
Just.
Okay, I'll see. Then in that case, I can arrange one. Only thing I'll have to write to you.
No, before Rekha
but she provides a Google form, which I have already filled up for the next session. Yeah.
Yes.
Okay, any other question?
We are also running out of time, so we will.
Okay. So because it's time now that thank you all for attending, and I hope I could clarify your doubts. If some of you still have some doubts, please write back, or you write in the forum, we'll reply back. Okay. Then see you till the next live session. Thank you.